The James Webb could have detected the first stars of the universe. Since the James Webb Telescope went live, it's taken incredible photographs of the universe, galaxies, nebulae, and stars. But what do these images tell us? Have we discovered new things? Are we close to impressive finds? Let's go. First discovery: the Sparkler Galaxy. The first science quality image revealed by the James Webb Space Telescope contained a treasure trove in the form of a sparkling distant galaxy surrounded by dense clusters that could contain some of the universe's first stars. The first deep field image from the James Webb Space Telescope, JWST, offered an impressive array of galaxies and galactic clusters that warp due to the effect of gravitational lensing. Gravitational lensing was first predicted in 1915 by Albert Einstein's theory of general relativity and has since become a powerful observational tool for astronomers. General relativity says that objects of great mass curve space-time. Think of this as placing balls of mass on a stretched rubber sheet. The higher the mass, the greater the curvature in the rubber sheet. Gravitational lensing forms when light from distant, bright objects bends around a massive object, such as galaxies and galaxy clusters located between the emitting and receiving object. In other words, gravitational lensing amplifies the light of distant objects. Thanks to this, we can see very distant objects even if they are extremely far away. A team of Canadian astronomers has focused their research on a galaxy 9 billion light-years away from Earth, dubbed the Sparkler Galaxy, because the compact objects surrounding it appear as small, bright yellow-red dots. The gravitational lens gives the Sparkler Galaxy its strange, stretched shape. The same phenomenon causes several surrounding clusters to appear at multiple points in the JWST deep field image. The surrounding objects that inspired the nickname are of particular scientific interest, as they could be the most distant globular star clusters ever found by astronomers. Globular clusters are collections of ancient stars that date back to a galaxy's infancy, so they may contain clues to the early stages of galactic formation, growth, and evolution. You can see the discovery of the team of researchers. On the one hand, we have the deep field of James Webb, and right in the middle, in the center left part, you can see a galaxy deformed by a gravitational lens, but around it are 12 mysterious points. Using the Hubble telescope as support, it is impossible to visualize the 12 points around the galaxy Sparkler, but they are seen with the James Webb. Looking at the 12 compact objects surrounding the Sparkler Galaxy, the Canadian team from the Near ISS Unbiased Cluster Survey, CAN-UCS, found that 5 are globular clusters. In addition, these could be some of the oldest globular clusters ever seen, perhaps dating back to the time when the universe began generating stars. Using such distant globular clusters to date the first stars in the early distant galaxies was impossible before James Webb. Hence, it is a new and exciting discovery for the scientific community. The Milky Way contains about 150 globular clusters, but scientists are still working hard to determine their ages. While it is relatively easy to date the age of most things in our galaxy, this is not the case for particularly ancient objects, which already look old when we viewed up close. This is because these objects have been around for a long time, and we have no information on how they were in the past. It is much easier to date more distant clusters like the Sparkler Galaxy, since astronomers see it as it was 9 billion years ago, when the cluster was much younger and the universe was only 4.5 billion years old. Are these stars the first to form in the known universe? For now, it's very hasty to say it, but according to the investigations, little by little we will discover the oldest stars in the universe. For now, it only remains to continue studying the images provided by James Webb. Second discovery: Spiral Galaxy IC5332. This is the Spiral Galaxy IC5332. On the left side is the view with the Hubble Space Telescope, and the right side is the view with the James Webb Space Telescope. The images show the powerful capabilities provided by both world-leading space telescopes, especially when combining their data. The Galaxy IC5332 is located more than 29 million light-years from Earth and has a diameter of about 66,000 light-years, making it 1/3 smaller than the Milky Way. It stands out for being almost perfectly facing the Earth, allowing us to admire its spiral arms' symmetrical movement. James Webb observed this galaxy with its mid-infrared instrument, also known as MIRI. This is the first instrument to easily offer mid-infrared images that are sharp enough to match Hubble's view at shorter wavelengths. This extravagantly detailed mid-infrared image is juxtaposed here with a beautiful ultraviolet and visible light image of the same galaxy, created with data collected by Hubble's wide-field camera. When comparing both images, some critical differences jump to the eye immediately. The Hubble image shows dark regions that appear to separate the spiral arms, while the Webb image shows a continuous tangle of structures that echo the shape of the spiral arms. This difference is due to the presence of dusty regions in the galaxy. Ultraviolet and visible light are much more likely to be scattered by interstellar dust than infrared light. Thus, dusty regions can be easily identified in the Hubble image as the darkest regions through which much of the galaxy's ultraviolet and visible light has been unable to travel. However, those same dusty regions are no longer dark in Webb's image, as the galaxy's mid-infrared light has been able to pass through them. Different stars are visible in the two images, which can be explained by the fact that certain stars shine brighter in the ultraviolet, visible, and infrared regions, respectively. The images complement each other in remarkable ways, and each tells us more about the structure and composition of IC 5332. It is incredible the enormous differences that can be observed when we look at the same galaxy with the two telescopes. When comparing them, it seems that we are looking at two completely different objects. If this can be achieved by looking only at a galaxy, can you imagine what we can get when we look at the entire universe? Collaboration between James Webb and Hubble for the DART mission. A few days ago, NASA carried out the experiment to deflect an asteroid with the DART mission. NASA scientists and engineers took this opportunity to test the capabilities of the two most powerful telescopes of the moment, Hubble and James Webb. Both telescopes captured unique images from NASA's Double Asteroid Redirection Test, DART pack, making the first time Webb and Hubble were used to observing the same celestial target simultaneously. On September 27, 2022, DART intentionally crashed into the asteroid Dimorphos, the asteroid's small moon in the Didymos double asteroid system. It was the first test in the history of kinetic impact using a spacecraft to deflect an asteroid by modifying its orbit. DART is a test to defend the Earth against the possible dangers of asteroids or comets, and according to measurements, it has been an unprecedented success. The observations are more than an operational milestone for every telescope. There are also critical scientific questions related to the composition and history of our solar system that researchers can explore by combining the capabilities of these observatories. The Webb and Hubble observations will allow scientists to gain insight into the nature of Dimorphos' surface, how much material was ejected by the collision, and how fast it was ejected. In addition, looking at the impact over a wide range of wavelengths between Webb and Hubble will reveal the particle size distribution in the expanding dust cloud, which will help determine whether it spewed out many large chunks or mostly fine dust. The composition of this information will help scientists understand how effectively a kinetic impact can modify an asteroid's orbit. Observation with James Webb. Webb observed the impact location before the collision occurred, then several observations over the next few hours. Images from Webb's near-infrared camera, NIRCam, show a tight, compact core, with plumes of material appearing as scrolls moving away from the center where the impact took place. Observing the impact with James Webb presented the flight operations, planning, and science teams with unique challenges due to the asteroid's travel speed through the sky. Teams worked in the weeks leading up to the impact to enable and test a method of tracking asteroids, moving more than 3 times faster than the original speed limit set for Webb. Thankfully, everything went according to plan. Webb observed the impact for 5 hours in total and captured 10 images. Observation with Hubble. Hubble also managed to capture observations of the small moon before the impact, then again 15 minutes after DART collided with the surface of Dimorphos. Images from Hubble's Wide Field Camera 3 show the impact in visible light. The ejecta from the impact appears as rays extending from the asteroid's body. The flared ejection peak to the left of the asteroid is where DART impacted. Some of the rays appear slightly curved, but astronomers must look closer to determine what this might mean. In the Hubble images, astronomers estimate that Didymos's brightness increased threefold after impact. They are also particularly intrigued by how that brightness remained stable, even 8 hours after impact. Hubble will monitor Dimorphos 10 more times over the next 3 weeks. As the ejection cloud expands and fades over time, these periodic, relatively long-term observations will paint a complete picture of the cloud's expansion from ejection to disappearance. When comparing the images obtained from both telescopes, slight differences can be seen, mainly in the size of the particles that each could detect. James Webb is more sensitive to detecting smaller particles, so its images have a more significant presence of materials than those of Hubble. In addition, something that intrigues astronomers a lot is that after the DART impact on the asteroid, a tail very similar to that of comets was formed. This is due to all the dust that was ejected in the impact formed a tail of materials that extended for more than 10,000 kilometers. No one expected this, meaning that DART's impact on the asteroid caused more damage than everyone anticipated. Fortunately, we know that the asteroid Dimorphos is harmless to Earth, since it is trapped by the gravity of its parent asteroid Didymos, so there's nothing to worry about. The Earth is safe. As we can see thanks to the James Webb Space Telescope, we are obtaining impressive images that are helping us reveal incredible mysteries of the universe. And this is just the beginning. What do you think will be the subsequent discovery of James Webb? Let us know your opinion in the comments.